dinosaurs ever set foot on Earth. Our side of the family tree had already built an empire. Sail-backed predators stalked open floodplains. Herds of tank-sized herbivores shook the ground. Saber teeth flashed on animals that had never worn a single reptile scale. Then, almost all of it vanished. So what did the world actually look like when the mammal side of the family ruled? Before mammals even existed. When most people picture prehistoric Earth, they jump straight to dinosaurs. Tyrannosaurus, Triceratops, steaming Jurassic forests. But the world that made the dinosaur age possible came millions of years earlier, and almost nobody talks about it. It's called the Permian. It began around 299 million years ago, the final chapter of an era called the Paleozoic. It ended in the worst mass extinction this planet has ever recorded. Dinosaurs weren't ruling yet. Mammals, in any form you'd recognize, didn't exist. But synapsids, our side of the family tree, were already spreading into every role a modern ecosystem needs. Herbivores, apex predators, burrowers, even climbers. This was the first time in Earth's history that a single evolutionary lineage had managed to do that on land. Every major role filled at once in the same world. Over the next half hour, you'll watch a swamp world collapse into ice. You'll watch continents lock together into one supercontinent. You'll meet a sail-backed hunter everyone mistakes for a dinosaur, an animal stranger than anything Hollywood has ever put on screen. And eventually, you'll watch a planet turn against everything living on it. To understand how that world looked, we first have to watch an older one fall apart. Rewind past the start of the Permian, into the tail end of the Carboniferous, about 340 million years ago. Picture the ground itself working against you. Shallow roots tangle across rotting logs. Moss coats every surface in a slick green film. Something with too many legs disappears into a gap in the bark before you get a good look at it. This is a hot, swampy, waterlogged world, covered in forests unlike anything alive today. The tallest trees aren't really trees in the modern sense. They're relatives of horsetails and club mosses, grown to an absurd scale. One genus, Lepidodendron, could tower over 130 feet, with a trunk more than 6 feet across. It was built from a light, springy kind of wood that let it outgrow everything that came before it. These forests grew, died, and grew again, burying layer after layer of plant matter faster than it could fully break down. Scientists used to say that happened because fungi capable of digesting tough plant fiber simply hadn't evolved yet. The real story is more complicated. These wetlands were exceptionally productive, and the sediment, the waterlogging, and the burial conditions were exactly right for locking carbon away for good. 90% of all the coal we've ever mined comes from this one narrow window of time. Every lump of it, sitting underground for over 300 million years, until something eventually figured out how to burn it. That burial mattered far beyond the forest floor. Every ton of carbon locked into coal was a ton pulled straight out of the atmosphere. And carbon dioxide is what keeps this planet's climate from sliding into deep freeze. Pull enough of it out fast enough, and you don't just change the weather. You change the rules the entire biosphere has been playing by. But the same drying, cooling shift that would eventually break these swamps apart was already creating a problem and an opportunity. Most tetrapods back then still needed standing water to breed. Their eggs would suffocate or dry out anywhere else. That meant something enormous. A vertebrate could finally walk away from the water's edge and keep going. Pull back from ground level, and the whole planet looks different. By the Permian, the continents had jammed together into a single landmass, Pangaea. One vast ocean, Pangaea, wrapped around the outside of it, while a smaller sea, the Paleotethys, cut into its eastern coastline. Pangaea wasn't one giant desert, even though that's the image most textbooks leave you with. It was a machine for manufacturing extremes. A mountain range running through the continent's interior blocked moisture from reaching deep inland. It's the same rain shadow effect you can see today on either side of the Himalayas. Coastal regions caught seasonal monsoons, the far interior baked dry, and down in the southern half of Pangaea, glaciers still gripped huge stretches of land, left over from an ice age earlier in the Permian. That gave this world an enormous range of habitats. Glacial margins, windswept highlands, river floodplains, parched interior basins, patches of seasonal forest, all on the same supercontinent, sometimes only a few hundred miles apart. A single overland walk could take you from a glacier's edge to a monsoon forest, to a bone-dry basin, without ever crossing an ocean. In a world where water was becoming less predictable, which animals were suddenly holding the better hand? The amniotes, animals that didn't need a pond to reproduce, were free to spread into places their ancestors never could. And within that group, one branch in particular was about to become extraordinarily successful. That branch had a poster child, and you've probably seen it without knowing what it actually was. Dimetrodon shows up in dinosaur toy boxes and cartoon lineups constantly. It's got the sail, the long tail, the reptilian sprawl. But Dimetrodon lived tens of millions of years before the first dinosaur ever walked. And it sits on the synapsid side of the family tree, genetically closer to you than to any lizard. 3 things made it dangerous. First, it hunted. Second, its teeth weren't all identical, the way a lizard's or a crocodile's are. Some were built for gripping, others for slicing. An early hint at the specialized dentition that would later define mammals. Third, that sail on its back. We still don't fully know what it was for. Thermoregulation has been proposed, flooding the sail with blood to soak up heat and warm the body faster. Display has been proposed too, a signal to rivals or potential mates. It may well have done both. Paleontology hasn't settled the question, and it doesn't need to for the sail to be remarkable. In 2025, researchers studying early Permian body impressions from a site in Germany found something rarer than a skeleton: traces of the actual skin. Small, overlapping scale-like structures, pressed into the stone alongside the body outline. A separate 2026 study looked at a smaller German relative, Dimetrodon teutonis. It grew up on a completely different schedule than its North American cousins. Proof that even closely related predators could follow very different life histories, depending on where they lived. Dimetrodon was impressive, but it was only the opening act. Plants are an enormous energy source, but they're a hard one to unlock. All that fiber has to be broken down before it's worth anything. Diadectes was one of the first large-bodied animals on land to manage it, chewing through tough vegetation other tetrapods couldn't touch. That mattered enormously to whatever was hunting it. A big herbivore isn't just an animal, it's plant energy, concentrated and repackaged into a slow-moving, several hundred-pound meal. A 2026 study looked at 3 juvenile Diadectes skeletons from early Permian Texas and found something predators had left behind: bite marks. For a world this far removed from us, actual evidence of behavior is rare. But sometimes behavior leaves a mark directly on the bone. Once large herbivores filled the landscape, what was going to stop the predators from getting bigger, faster, and more specialized too? Nothing. This is where things start moving fast. Research tracked a major shift in how carnivorous synapsids fed between the early and middle Permian. Jaws grew built for either raw bite force or blazing speed, evidence of a predator-prey relationship escalating on both sides at once. A 2026 study went further, showing that Permian synapsid skulls were being reshaped by diet and selection far more than by ancestry alone. Watch what that actually does to bodies. Prey get heavier. Some grow armor-plated. Limbs shift under them to carry the extra weight. Predators grow deeper skulls for crushing bite force, or leaner ones built for a fast strike. Canines lengthen. A few lineages start experimenting with something close to saber teeth. And a new group starts pushing the older synapsids aside entirely, the therapsids. Some of them are dinocephalians, massive, thick-skulled herbivores. Some are apex predators like Ankylosaurus, a 500-kilogram killer with a bite built to bring down the biggest animal in its ecosystem. And researchers described a Gorgonopsian from Mallorca that may be the oldest one ever found, possibly the oldest therapsid, period. It lived near the equator, in tropical Pangaea, a region the fossil record has mostly ignored. A 2026 analysis backs up the same picture, therapsids appearing early, then exploding outward fast. For the first time, land-supported predators and prey locked into a genuine evolutionary contest. And just as that contest hit a new level, the cast changed again. Take a breath. Not every corner of the Permian was a battlefield. Along the coasts and inland lakes, Mesosaurus paddled through the shallows, one of the earliest amniotes to head back into the water. Its fossils later became one of the strongest pieces of evidence that the continents had once been joined into a single landmass. Further inland, Scutosaurus grazed in herds, a heavily built, armor-plated herbivore, roughly the size of a rhinoceros. It belonged to a completely different branch of the amniote tree than any synapsid around it. And up in the canopy, something almost nobody expects from this period, Coelurosaurus. This small reptile had evolved elongated rib-like rods under its skin, spread out like a fan. It could glide between trees, tens of millions of years before anything resembling a bird existed. Meanwhile, out past the reach of the coastline, ancient trilobites still drifted through Panthalassa. They were the last members of a lineage that had been swimming these oceans since before complex animal life had even colonized the land. Their best days were centuries behind them, but they were still out there. A living relic, drifting through a world that had otherwise moved on without them. Synapsids were holding most of the headline roles in this world, but they never had the continent to themselves. Quietly, in the background, the lineage that would one day give rise to dinosaurs was already spreading and experimenting, waiting for its own turn. So why call this a lost age of mammals at all? Because therapsids weren't just getting bigger or scarier. They were trying on almost every body plan the mammal lineage would ever use again. Take Moscops, a dinocephalian built like a barrel with a skull thick enough to survive repeated head-on impacts. Researchers suspect it may have used that skull in contests of strength or dominance, though exactly how those clashes played out is still debated. Then there's Pterogodens, an herbivore roughly the size of a capybara, carrying a pair of enormous, saber-like canine teeth. Not for hunting, almost certainly for fighting other Pterogodens, over territory, mates, or status. It's a strange thing to process. The first known saber teeth on this planet may not have belonged to a predator at all. And then there's Suminia, a small, big-eyed animal with an unusually long, opposable-like fifth digit and grasping fingers. It's long been interpreted as one of the earliest tree-climbing tetrapods on record. Its limb bones were unusually light for its size, compared to related animals. That reinforces the idea that it spent its life above the ground, rather than on it. Long before squirrels, long before primates, long before true mammals existed at all, one branch of this family tree was already living in the trees. If synapsids could become giant grazers, saber-toothed herbivores, tree-dwelling climbers, and apex predators, how close was this world actually getting to something we'd recognize as mammalian? Close, but not there yet, and not in the way you'd expect. Late in the Permian, a new group of therapsids appears, the cynodonts. Don't picture them as tiny modern mammals in disguise. What's actually happening is stranger, and honestly more interesting. It's mosaic evolution. Individual mammal traits show up piece by piece, in different lineages, at different times, not all at once, as a finished package. Teeth specialize further, splitting into distinct types built for cutting, piercing, and grinding, instead of the one-size-fits-all row you'd find in a lizard. Jaw structure shifts. In several of these animals, a bony secondary palate develops across the roof of the mouth, physically separating the nasal passage from the mouth. That sounds like a minor architectural detail. It isn't. It meant an animal could breathe and chew at the same time, a small change that would eventually help make nursing possible. There's also fur to consider. The science stays cautious here on purpose. Speculation is cheap. Fossils aren't. We've talked about these animals through their bones so far, what their skulls, teeth, and limbs were capable of. Now it's worth asking what they actually did with any of it. In 2026, researchers described something unusual out of early Permian Germany, a regurgitolite, fossilized material an animal swallowed, then brought back up. Inside it were 41 identifiable bones from multiple prey animals. Nobody can say for certain which predator produced it, though several of the large hunters already known from this ecosystem are reasonable suspects. Sometimes the most revealing fossil isn't what survived inside an animal, it's what failed to stay there. Line up the evidence, and you start to see three completely different windows into the same world. Skull anatomy tells you what a predator was capable of eating. Bite marks on bone tell you what it actually fed on. And something like this tells you what it swallowed, chewed, and couldn't keep down. Put together, paleontology stops looking like a pile of bones and starts looking like an actual investigation. Skin, growth rates, bite marks, stomach contents. But one set of rocks, laid down at the very end of this world, records something much bigger than any single meal. It records the failure of the entire system. Near the close of the Permian, in what's now Siberia, the ground itself started coming apart. Massive volcanic eruptions, what geologists call the Siberian traps, poured out an almost unimaginable volume of lava and gas. All of it over a relatively short stretch of geological time. The evidence points to this event as the main trigger behind what happened next. It wasn't as simple as volcano erupts, world dies. It was a chain reaction. Carbon dumped into the atmosphere at a staggering rate. The planet's greenhouse system overloaded. Temperatures climbed. Rainfall patterns broke down. Plants, already under stress, died back. That triggered erosion, which dumped nutrients into rivers and oceans, starving the water of oxygen and destabilizing food webs from the bottom up. Chemical evidence and climate modeling point to something even more unsettling. Intense El Niño-like conditions may have amplified much of that climate chaos. These extreme swings piled even more instability onto everything the volcanoes had already set in motion. It wasn't one simple cause, and nobody is claiming El Niño alone drove the disaster. But it reveals what mattered most to the animals living through it. The climate itself was becoming violently unpredictable. Rainfall stopped being reliable. Heat stopped being escapable. Every seasonal rhythm this ecosystem had adapted to over tens of millions of years started breaking down at once. Animals that had spent 50 million years learning to read a predictable landscape. How do you survive when the danger isn't a predator anymore, or even a drought? It's the entire climate system your ecosystem was built around. The first half of this story had monsters in it. This half has absence. Empty stream channels, collapsed vegetation, dead standing wood that never got the chance to rot properly. Fewer footprints in the mud each year, water gone dark and still. What followed is still, to this day, the worst mass extinction the animal kingdom has ever recorded. And it wasn't instant everywhere. Regional evidence suggests the collapse on land played out messily, in fits and starts, not as a single clean line across the whole planet. As vegetation died off, erosion across the land accelerated, washing more and more phosphorus into rivers and eventually into the oceans. That nutrient surge helped strip huge stretches of water of oxygen, pushing already stressed marine ecosystems even closer to collapse. But the rocks preserve something else too, a gap of roughly 50,000 years. That separates the first major disruption to the carbon cycle from the worst of the warming that followed. Land and ocean weren't separate victims of this disaster. Damage in one system spilled directly into the other, turning a planetary crisis into a self-reinforcing chain reaction. Think back to everything you've seen in this vanished world: the saber-toothed herbivore, the tree-climbing anomodont, apex predators built for crushing bites, animals experimenting with fur, specialized chewing, and breathing while they ate. Nearly all of it vanished, or was reduced to almost nothing. In the end, dominance offered no protection when the entire world changed. Out of that wreckage crawls Lystrosaurus, and this is not a triumphant return. The first landscapes of the Triassic aren't paradise. They're recovery wards. Nobody's found one clean explanation for why Lystrosaurus made it through when almost nothing else did. It was probably a combination. Wide tolerance for different conditions, a broad geographic range before the crisis even hit, physiology suited to hard times, and a fair amount of plain luck. And it wasn't alone. Alongside the dicynodonts and cynodonts that survived, several therocephalian lineages made it across the boundary too. Synapsids hadn't disappeared, but the world they used to run had. Sauropsids, especially the archosaur lineage that would eventually include dinosaurs, started pushing into the empty space left behind. Dinosaurs didn't walk in and take over immediately. That part of the story takes millions more years. So did the Permian extinction end the first age of mammals? Or did it just interrupt a story that would take another 200 million years to finish? It ended the Permian world synapsids had built. It didn't end the synapsid lineage itself. Descendants of those small burrowing cynodonts eventually gave rise to the first true mammals. And much later, after another mass extinction cleared the non-avian dinosaurs out of most large land niches, mammals got their own turn at building an empire. Nobody can prove the Permian extinction was somehow necessary for either group to exist. That's a counterfactual nobody can actually test. What we can say is simpler. It redirected the ecological history both lineages were shaped by. The Permian was never literally an age of mammals. What it actually was might be more interesting than that. It was a lost world where the broader mammal lineage had already become giant herbivores, specialized predators, climbers, burrowers, genuinely sophisticated animals, tens of millions of years before anything we'd call a mammal existed. Then the world changed, and almost everything changed with it. Every animal you met tonight was, in its own way, a rough draft. Evolution doesn't crown permanent winners, it only produces survivors of whatever world happens to exist right now. If you like rebuilding worlds that vanished hundreds of millions of years before ours, subscribe, because this story isn't finished. The extinction opened up enormous ecological space, but dinosaurs didn't just walk in and take it. For millions of years, other reptiles looked far more likely to inherit the Earth. So how did dinosaurs actually win?